curvature. That's like every topic we cover in this course talks about arc length at some point. So we did it for polars, parametrics, and now for vector valued functions. And then when we get into surfaces, we'll talk about lengths along a surface. So yeah, it's all fun. All right, to learn to find the arc length for vectors in free space, that's why we're here. All right, but also we're going to have to compute what's known as a unit tangent vector. And then we're going to figure out curvature. Curvature sounds fancy. It actually is a pretty cool concept, but really it's a number that represents the curviness of a particular graph. All right, so you think about that for a second. If I tell you that, and there's a nice Greek symbol to represent curvature. If I tell you that there is a number that can be applied to a particular function's graph that would represent how curvy it is, and then I ask you to tell me what that value would be for a line, what do you think the curvature number would be for a line? Zero, right? That's an easy one, right? Because it's not curvy at all. As you move away from being linear, your function gets curvier and curvier. What kind of figure do you think is the curviest? A circle, right? So you kind of have a sense of parameter, right? So if you know that the least curvy thing is a line and the curviest thing is a circle, everything else is going to fall in between.
How curvy is like the inverse of a circle?
The inverse, so a hyperbola?
Yes, yeah.
We could figure it out. Well, actually, that's not true. Well, maybe we can. Because usually it involves hyperbolic functions, which has been completely stripped out of Calc 2 and Calc 3. But we can do it with a function-based hyperbola. So I just got to think about how I want to do that. I will continue to think about how I want to do that. But I'll come up with something.
So then you said it's the range from 0 to as curvy as a circle. So what would that be? Would that be pi? Would that be 2 pi?
That is the question.
Would it be 1?
That is the question. We'll get there. We'll get there. But anyway, in order to really kind of tackle this, we need to get through the other stuff, which is the arc length and the unit tangent vector, because that's how we're going to figure out the measure of the curvature. All right. And conceptually, it's pretty cool stuff too. So all around. So arc length should look pretty familiar. It's just the expansion of the arc length formula for parametrics. Right? It's just we're in 3 dimensions, so we have the extra component. Right? So the good news is now that we've talked about vectors, we can simplify this integral to make it a lot more convenient. Because as you increase dimensions, this radical is going to get longer and longer. If we could have a nice simple way to represent it, then that would be a good thing. Right? But if you really think about it, R of t is defined as f of t I plus g of t j plus h of t k. The derivative of R of t would be the derivative of each component. That's what we were talking about previously. All right? So really all this would be, it's the square root of those sums. So it's really talking about the magnitude of your derivative function, your derivative of R of t. All right? So it's a nice, concise way of representing the arc length formula in any dimension, any set of dimensions. All right? So if I went out to 10 dimensions, this rule would still be true. All right? We just need to know where we're starting and stopping. All right? So that's going to be part of the challenge. But at least in terms of simple cases, it's not bad at all, because in number 1, it's just saying, really use the formula to get the arc length. They gave us a particular domain. We know generally, I mean, I use software to generate this picture. And if you remember from last class, I did it by hand. They both look pretty awful. So that's kind of how I justify the shoddy quality of my drawing. It's like, hey, look, a computer didn't do much better. But you did see on GeoGebra that there is technology that's really capable of making it look nice. It's just I couldn't get GeoGebra to make it look the way I wanted it to. So all I want to do here is find on the appropriate interval from 0 to 2 pi. I believe it was 2, yeah. The magnitude of r prime of t, dt. All right, and so that's going to be same integral, 0 to 2 pi, or the same bounds anyway, the square root of the derivative of each part squared. So cosine t becomes negative sine. It's going to be squared anyway, so if you forgot the negative, it's not the end of the world. / I wouldn't have noticed it anyway when I was grading your papers. I'm very comfortable admitting my failings. Probably a little too comfortable, but that's all right. Somebody told me a while ago, said that he thought I was a good teacher, thought I was, actually said it was the best teacher he ever had, which is always a good way to start off a conversation with me, by the way, in case you're wondering. But he said something that stuck with me. At first, I got kind of offended slightly, but then I realized what the message was. He said, you make it safe for me to make mistakes in class. Like, I feel comfortable going for it, and even if I get it wrong, I know that there won't be any judgment. Because you make mistakes all the time, and you're completely all right with it. I was like, oh, thank you so much. He's like, no, I didn't mean it that way. And I was like, I know what you meant, and I thank you for that. But yeah, so that's I always go back to that whenever I screw something up. It's like, there's one person in this world that's all right with it. So everyone else be damned. I don't even care. Square each part. At first glance, this looks like it might be terrible, but then you realize, nah, I don't want to do this on a calculator.
Why not?
I want to do this by hand.
Yeah.
Although my DT is like in no man's land now. All right, well, anyway.
Did you lose the negative in front of the sign?
It's squared away.
Squared? Squared away.
Yeah, when you multiply negative signs. So, quick question. What is sine squared plus cosine squared equal to? 1.
Beautiful.
All right, so 1 plus 1 is 2. So this is the square root of 2t. All right? Which has it's constant, so that has an antiderivative of root 2 times t over the interval of 0 to 2 pi, which means that it would probably take longer to type it in the calculator than it would to actually do it by hand. However, if you don't know that sine squared plus cosine squared is equal to 1, then by all means put it in your calculator because you'll have no chance of getting it right. Yeah, it would be a nightmare. You'd have to do substitutions. You'd have to replace this one with 1 minus cosine 2t over 2, and then 1 plus cosine 2t over 2. Simplify it, get a common denominator if needed, and then go from there, and it still wouldn't be pretty. But in this case, not bad at all, right? 2 root 2 pi. Or 2 pi root 2. As long as it doesn't look like the pi is under the radical, I don't really care how you write it. Right. And so these are linear units. So based on the context of the problem, you'd indicate what the units are. Meters, feet, miles, whatever. But that's what the length of this curve would be. All right, so this length from, assuming that this is an accurate diagram, which is hit or miss. This would be that. Right, so off the top of my head, let's see. So 1, 2, 2, 3. So we're looking at like somewhere around 8.
It's 8.88.
A little off. Yeah. So if you had to round it to the nearest whole value, you might go to 9. But you know, out of context, it doesn't really mean much. But we do know, based on graphing this last class, what this figure is supposed to look like. Right? Because we graphed an elliptical helix, and this is one where we're dealing with the x and y components is just cosine and sine, no coefficients, so we're dealing with a circular helix, right? So it's basically, if you think of a slinky, just stretch that bad boy out, that's really what you're talking about, right? So, but it's only going over an interval of 0 to 2 pi, right? So it's a minimal length, right? So having a small arc length kind of makes sense. All right, so number 2 is along the same line, so that's nothing unique, so I'll just put a star on that. But now we're going to talk about the intersection of two cylinders. So 3-dimensional surfaces. Path that I'm looking for. All right, so let's start with that. We have x squared plus y squared equals 9. We have y squared plus z squared equals 1. Speaking of substitution, that happens to be the way that we want to go generally. Elimination of a variable would be a reasonable approach. So I'm going to rewrite. I'm going to leave the first one the way it is. The second one, I'm just going to change it up. I'm going to negate everything and then swap the order of z squared and y squared. So negative z squared minus y squared equals negative 1. Same equation, different ordering, and also negation. All right, but when I add them together, I get x squared minus z squared equals 8. All right, so we have a relationship between x and z, and that's perfectly fine. All right, so I could solve this for x in terms of z. So x squared would be 8 plus z squared. All right, I can take the square root and get x equals the square root of 8 plus z squared. All right, so I have an equation solved for x in terms of z. All right, so it looks like I want to have an equation solved for y in terms of z also. Fortunately, that's kind of set up for me already, so I could snag that. So I'm going to take that equation and solve for y. So y would be equal to the square root of 1 minus z squared. All right, the only thing that's missing is a relationship between z and z. All right, because I have a relationship between x and z, a relationship between y and z. I need a relationship between z and z. Well, that's easy enough because z is the same as z. So z equals z. That's my free variable. That's the variable that could be anything. If I had 3 equations with my 3 variables, then I could figure out what each one of them would be numerically. But what we're looking at is really an open-ended system. And so because of that, they're going to be defined in terms of a third variable that we call z. All right, so what we do is we let z equal some parameter t. You can let it be whatever you want, but when you're dealing with parametrics, we tend to want to let it be equal to t. All right? So x would be equal to the square root of 8 plus t squared. Y would be equal to the square root of 1 minus t squared. And z would be equal to t. All right, in vector value function form, whether it's ijk notation or component form, is up to you, but I'm going to go component. 8 plus t squared, comma, square root of 1 minus t squared, comma, t. All right, so I'm going to pop that into GeoGebra. I'll put it up to display in a sec. 8. Comma. I could have just used the root. Could also probably stop talking to myself. So the big challenge, let me just pull it up here. All right, so I put in my curve. I just used power notation. So x component, y component, z component, variable, and then I need just my bounds, all right, my bounds for t. So we want to be thinking about what the possibilities are. We are dealing with radical equations. So we want to be thinking about situations in which you would not have a negative under the radical. So in the case of 8 plus t squared, not a problem, right? Because you're adding 2 positive numbers in all cases. So that's fine. T could be whatever you want for the z component. But for the middle one, if it's anything bigger than 1 or smaller than negative 1, then you're going to have a problem, right? So I want to be between negative 1 and 1. So that's what I'm going to do in terms of my parameters here. I'm going to put it between negative 1 and 1. All right, and so that's going to create a graph, or at least a path. All right, and so visually, it seems to be the path of a semicircle. All right, which ought to make sense because anytime you solve a circle equation, you know, just thinking back to algebra, you solve a circle equation for y. If you solved it the wrong way, you would get just the top half of the circle when you put it in your calculator. All right, so if I said you had x squared plus y squared equals 1, and I told you to solve for y, and you told me y equals 1 minus x squared under the radical, what was I missing? The negative sign, because when you take the square root, it should be plus or minus. All right, so that's what happened here. We didn't include the plus or minus, but that's okay because visually, it looks like I have 1/4 of what I want.
You mean 1/2?
No, 1/4 because there's 2 sides.
So you want both sides?
You want both sides. All right, so I have exactly 1/4 of what I want. So once I get this answer, if I multiply it by 4, I'll have what I need. All right, so state your domain, that's important. or at least being aware of it's important because it's going to come through the integration process. So t should be between -1 and 1. All right. So to find my arc length, I'm going to integrate over the interval of -1 to 1. And that's why I said you at least be aware of it, because if I don't state it there, it's fine. It's going to come through the integral anyway. All right. It's going to be the square root of the derivative of each of those parts. All right. And then we'll take that and multiply it by 4. I'll just pop the times 4 in the front. All right. So I need the derivative of each part. So at this point, based on our derivative, I'll just kind of cut to the chase here. We're looking at t squared, the chain rule applied to that would be 1/2 8 plus t squared to the -1/2 raised, multiplied by 2x, the 1/2 and the 2x, the coefficient of 2 would cancel out. So we'd be looking at a simplified form of this as a quantity squared, all right, because it's derivative squared, plus, again, 1/2 1 minus t squared to the -1/2, so that puts a square root of 1 minus t squared on the bottom, multiplied by the derivative on the inside, which would be -2t, but then multiply the -2 by 1/2, you get a -t. And what did I say over here? That should be just a t. All right. Squared plus the part that I'm least likely to screw up would be a 1 squared, which is just a 1 dt. Now we can clean this up if we want, or we could just chuck it right into the calculator. All right. And since each one of these represents a semicircle and we have a total of 4 semicircles, that's where the coefficient again is coming from. So after a lot of hocus pocus, end up with the hopefully correct result of about 6.329. So
actually, my answer's correct anyway, because even though I don't square the t, it's just a -1 or a +1. So if you square it, it's going to be 1 anyway.
right.
Yeah, but you have to get
Honestly, I mean,
well, no,
really,
0.5 and 0.5 squared are very different numbers, and
This
to
is
take
true.
the definite integral,
My calculator says
you have to, yeah, sure, the endpoints are like all fine and dandy, but like everything between it is getting messed up.
yeah,
by
that's a good
nonsense.
point. Yeah, and in reality, I think it's probably, I'd like to think that you would agree with this. I'll find out in a second, I'm sure. We satisfied the objective of the problem once we came up with the integral, because anything after that would be Calc 1, Calc 2. So really the new Calc 3 stuff was getting to the part where you came up with the integral. So I do that a lot in Calc 2, where it's show me the integral that you would use to come up with the volume of the whatever it is rotated around the x-axis. So it's the same idea here. Show me the integral that you would use to determine the arc length for whatever this figure is. All right, so think of it that way, because I would never on a test, definitely never on a test, put a problem on there where your calculator is going to flip out on you. All right, and then tell you that you could use your calculator. I'm not sadistic. All right, so, or at least not in this class. So I saved that for high school math. Watch them all bug out. It's great.
Just not working.
Oh well.
That's broken, I guess.
This actually said break, so. It actually said break. It's actually, I took a picture, I'll show you. It said break, go to it, quit.
Broken. Give up. No. Who do you think you are?
Don't
trying
even guess.
this
Don't do me like
nonsense?
that.
Just make an educated guess. So,
Skip this one.
so parameterizing a curve in terms of arc length, right? That's kind of a weird thing to think about, but if you actually think, well, about it in terms of the arc length. So, you know, you're normally talking about a parameter in terms of time. What if you're talking about a parameter in terms of position, right? So, like when I add that little component there, maybe that starts to help, because if I tell you that your position in space can be dictated not just by time, but by movement along a particular path, that might be more meaningful for you. So I'll just give you a quick example. You have a circular helix that I'll draw poorly. All right, and you have, and let's say your axes are way over here. You know, it's really out there in space. You're right here. All right, your movement along this curve, you know, it could be represented by passage of time. Right, and you can clock that. You can say an hour into my hike, I'm at that location. Right? That's a possibility. But you could also talk about your position relative to the amount of distance that you've traveled. Right? And what do I mean by position? I'm talking about coordinates, something, comma, something, comma, something else. All right, maybe even a vector. All right, so your position along this curve could be dictated by the amount of time that it took to get there. So where were you in your hike after an hour? Or where were you position-wise in your hike after you traveled 1 mile? So you'd say, okay, well, 1 mile is my position. Well, 1 mile from where? All right, if I give you a benchmark, if I tell you that this is a home base or base camp, what is your position relative to that location? All right, so then you start thinking about that, you get into applications involved in GPS, because you have the time component, how long it takes to complete a journey, your position along that journey, but also how far you've traveled in your journey. All right, so all three of those components can come into play. Right? So when you start getting into your physical position on the planet, that's a coordinate-based measure. But you're probably perceiving it in terms of time and distance traveled. I don't know too many people that are thinking it in terms of latitude and longitude and their height off of the surface of the Earth. All right? So, but then again, I don't know too many pilots. So that's just the reality of it. So there is value in being able to convert over from a time-based parametric to an arc length-based parametric. And it's really for this topic that we actually learn about arc length. You know, like I mentioned it before, we learned about arc length in polar form, parametric form, and now we do it for vector valued functions. It's like, wow, this arc length concept seems to be really important. Well, it is, but for ideas like this, physical characteristics. Anyway, this I think I really just addressed. To do this, recall textbook jargon, that for a curve given by the vector value function, we can define the arc length function as this. That's what we were just talking about. But we're going from some time t sub o to time t. So initial time to a variable time down the line. All right, so maybe you're starting off at time t equals 0, maybe it's time t equals 20, but some constant starting time, right, to a variable time t. Right? The antiderivative of that would have the same characteristics. You know, if you put it in the arc length form or if you put it in the magnitude form, it's going to be the same idea. But if you apply the fundamental theorem of calculus, we can actually play this out. If I were to find the derivative with respect to the variable s of the integral t sub o to t of the magnitude of r prime of u du you're going to get a completely different relationship. All right? So you're taking the derivative of an antiderivative of a derivative, right? Which is a really weird thing to think about. Right? So that's something that we're going to work towards understanding, but this is going to be the foundation of everything that follows. So we're going to play around with an example first, and then I'll come back to this rule. All right? So the integral relates arc length s to the given parameter t. So we're getting from this relationship, that's our arc length, to some parameter, or we're relating it to some parameter t. The idea is to evaluate the above integral to find s of t and invert the equation to obtain t of s, and then substitute t of s into the original parameterization to obtain arc length parameterization. Okay, so it's like words, right? So let's play this out and see what it looks like in action. Oh, that hurt. So let's find the arc length. Instead of going from 0 to 2 pi, which would be a finite set of parameters, I'm going to go from 0 to some variable parameter t. All right, so from 0 to t, because it could be at any moment over the interval of 0 to 2 pi. All right, so I'll just make a note of that. That is not me making a note of that. All right, so this is because you want to go to any time t on the interval of 0 to 2 pi. All right, so that's our justification for finding the integral over 0 to t. All right, now the rationale is going to be the idea that we can change our variables, but we'll get to that in a minute. All right. And also, just something to keep in mind, you might know a path is 10 miles long, but what I care about is my position along that path. I might only be 2 miles in. Right? You just think about a person running a marathon. You're tracking them on the app. Was it NYR? Whatever it is. But TD Marathon, the app, whatever the app is. But it tracks all the runners. Like, you know the length of the overall marathon, but you're tracking their position along the route. Right? So you don't care that the overall length is, what is it, 26.2? For a marathon? So, something in that neighborhood? Yeah, we don't care about that. We care about the fact that the person's on mile 2 and they got another 24 and change miles to go. All right? So let's figure out what this is going to be as a parameterized form. So square root of the derivative squared. All right? So a cosine t has a derivative. That is cosine, right? As a derivative of negative a sine t, quantity squared, plus a sine t has a derivative of a cosine t squared, dt. Oh, because it's allowing for a function within a function. So it could be a function.
So if these functions are defined as f of t, g of t, and h of t,
Oh, wait a minute. Oh, sorry. Hold on. That should be a du at the end. I thought you were talking about the functions within the parentheses. I missed that part. All right. So,
Shouldn't it be U?
Like, why are we making it U?
why are we
So if
making...
you go to the definition, it gives these functions in terms of t, and then changes them to a u.
Because we're integrating with respect to a completely different variable, and we're leaving that up in the air right now until we make our substitutions later on. So
integrating with respect to u.
we're integrating with respect to u. And then we'll make a substitution of t later on.
But then like in diffeaqs, aren't you supposed to treat the t's like constants or something like that?
That's if you're dealing with partial integrals. I'm sorry, multiple integrals. That's later on. Here we're doing a change of variables. It's a different concept.
Sine u and cosine u, and not sine t and cosine t, but like.
Oh, that. Okay. Yeah. Sorry.
That's what I was.
Yeah. Okay. Yes, they are used. I was looking at the wrong thing. Okay, so anyway, and also there was the component where it was all going to work out in the end, so I didn't even notice it. You'll see. So a squared sine squared u plus a squared cosine squared u du. A little bit of manipulation now is going to pay off in a few minutes. All right. We have a GCF of a squared that could be pulled out of the entire radical, right? Pull it right out and make it an a. All right, you factor out the a squared, but then take its square root, and it becomes an a. Next step in the process would be, so still 0 to t, a, I'll write the rest in a second. What's sine squared plus cosine squared? 1. Square root of 1 is 1. So it's really just going to be a du. All right. So we can integrate that and get au over the interval of 0 to t. All right. Now this whole thing is equal to s of t, but I could just write it as s. My substitution using the fundamental theorem, now this would be fundamental theorem part 1, would be s equals at. All right, so we have a relationship between s and t with some constant multiple a. All right, and that's really all we were looking for, because if I want to reparameterize, or you could even say deparameterize, it's a question of changing the parameter from one variable to another. It's in terms of t, I want it to be in terms of s. I now have a relationship between s and t. All right, so I can now say that t is equal to s divided by a. And that would make my new function how is it written? R of t. It was r of t. I'll rewrite it here and I'll just show it underneath. Was equal to originally cosine sine. Oh, a cosine. T, a sine t. All right, so I want to have it in terms of s. So I now know that t is equal to s over a. So if I want to parameterize in terms of s, it would be r of s, because my variable would be s, a cosine s over a, comma a sine s over a. All right, but all that work was for the purpose of getting the relationship between t and s. All right. Now, it may be a question of, okay, so if I'm replacing all the t's with s over a, why didn't I replace this t with an s over a? This is really defining what your function is in terms of. We're parameterizing here in terms of t, here we're parameterizing in terms of s. The relationship between s and t is not important. The fact that there is a relationship between s and t is what allows us to write this. But the independent variable that makes up my vector valued function is the parameter s. All right, so that justifies going from r of t to r of s. But since the relationship is that t is equal to s over a, we can make the substitution here. All right, so that would give us, provided that we know the information related to the a value, it would give us the ability to parameterize in terms of arc length. All right, so let's say I was dealing with a circle, because this is really a circle equation, right? Because coefficients are the same, a and a. If this were a and b, then we'd be looking at something that was elliptical, all right? Because they're the same, we know it's circular. So let's say it had a radius of, well, or I'll just say an a value, but that would correspond with the radius. It had an a value of 4. I now know that time is equal to the arc length divided by 4 if the a value is equal to 4. All right? Or you could think of it this way. The arc length is 4 times the movement of time. So if you really think about it that way, depending on what the units are for arc length, let's say you're going in terms of feet, that's telling you that for every second, for example, you would be moving 4 times that amount, so 4 feet. Right? So you have a relationship between, in that case, seconds and feet that you can use to define your vector, right? Your vector value function. Right? So it allows you to come up with that relationship. This one works in general terms, and I don't know that this should necessarily be the next question. There really should be a question in between. Instead of going from not too bad to holy moly, what is this? So I'll take that as a typo. Create new question, or create additional question, a new question 5, and make 5 question 6. All right, but we're gonna tackle another question along these lines in a second. Just we'll come back to this one after we do that, because. All right, so we want to parameterize in terms of s. All right, so we'll assume the same domain considerations. So t is between 0 and really something else. It doesn't matter, but I'll say 2 pi. All right, so s of t is going to be equal to 0 to t. All right. And if you have some other initial value, depending on the nature of the problem, it might not be 0 to start, but you know that would be particular to whatever question you're dealing with. Square root. Now these are the derivatives, so just comparing to what we did, we found the derivative of each part in terms of u, right? And then we went through the process from there. So that's what we're going to do here. So a lot of similar characteristics. So the derivative of 2 cosine t would normally be negative 2 sine t, but it's going to be negative 2 sine u. Plus derivative of 2 sine t would normally be 2 cosine t, but this time it'll be 2 cosine u. And the last component has a derivative of 1 in terms of u is still 1. So we'll still write it as squared du. All right, so we're looking at the square root of 4 sine squared u plus 4 cosine squared u plus 1 du. All right. The issue for this one is you can't just pull a 4 out of the whole thing, but you can still pull a 4 out of part of it. So 0 to 2, 0 to t, 4 times sine squared u plus cosine squared u, that's the nice part, plus a separate one, du. And we know that sine squared plus cosine squared is equal to 1. So the 1 times 4 is 4 plus 1 is going to be 5. So we're looking at root 5 du, which has a derivative of root 5 times u over the antiderivative, over the interval of 0 to t. So what we get is a relationship where s is equal to the square root of 5 times t. And since ultimately my goal is to swap out the t's in my original vector value function for s's, I would solve this for t in terms of s, and then make my substitutions. So I'd be looking at r of s instead of r of t. It's going to be equal to 2 cosine s over the square root of 5, comma 2 sine s over the square root of 5, comma, instead of the last one was just a t, so just s over the square root of 5. All right, so what we get from this, same idea as the last one, but it has real numbers in it, so, or at least particular values. You can see the relationship a little bit better, is that arc length moves at a value that's radical 5 times whatever the value of time is. All right, so for every 1 second increase in time, you're going to have a radical 5 increase in arc length. All right, so it's a proportional relationship, but now we have a function that's defined in terms of the arc length rather than the amount of time that's elapsed, all by knowing the relationship between the two variables. All right, but we only get the relationship between the two variables by carrying out this process. Okay. Weird process, definitely, but a necessary one, as you'll see moving forward, because curvature doesn't happen without this concept.